Okay, we're live. Hello, everyone, and welcome to the Virtual Jug. I think I was actually looking at the meetup site today. I think we were on around 100 meetups now, so this is a fairly big milestone for the Virtual Jug. So joining me today on the Virtual Jug, as usual, my fellow V-Jugger, Oleg Shlev. How you doing, Oleg?
Hey people, I'm doing great. Excited to be here.
Awesome. And giving today's session, Mr. Chris Seaton. How are you, Chris?
Good, thanks. What are you doing here in Cheshire, though?
You're in Cheshire. I was going to say, whereabouts are you calling in from today? Cheshire. Yeah. It is hot, isn't it? I'm down in Basingstoke, just south of London, and it's. I have no idea what the temperature is, but it's. It feels like we're well into the UK summer. So, Chris, what are you going to be talking to us about today?
I work for Oracle Research, which is the research arm of Oracle. We're looking at new ways to do polyglot programming. So people who want to use more than one language in the same project, how can we do that on building on top of the JVM? How can we make that fast? And how can we do things we couldn't do with it before?
Mm-hmm. And I called you Mr., but you're actually a doctor, aren't you?
Yeah, so I come from academia. Oracle Labs it's a bit like an academic department within Oracle. We get to do similar sort of research and we get similar amount of freedom. It's an excellent setup.
Okay, awesome. Well, we're looking forward to your session today. But first, what I'm just going to quickly do is go through a couple of things that will help people ask questions. So we're going to go through some slides and watch a demo as well. If you have any questions, please feel free to ask them directly into IRC. We have the hash or pound virtual jug chat, which is a channel which is on Freenode. You're also welcome to tweet to us and all kinds of things like that at Virtual Jug. What else? So the session's gonna go on for about 45-50 minutes. Chris, would you like questions during or after?
Yeah, during's good. It's easier to do questions in this format than it is in a big room, so it's a good opportunity.
Okay, so awesome. So ping us those questions then, and you won't need to check IRC. Chris will interrupt when we can. Great. And ask questions as we go. One other thing, actually, I'll very quickly just show you if I quickly share my screen, is we made an announcement today. You may have seen it on your email just moments ago. And can you see my screen? Looks like you can. This is Virtual Jug 24. This is actually the second edition of this conference. It's a 24-hour virtual conference, virtual Java conference. And essentially everything's open now. So if you want to, hang on, let me just click on VJug 24. If you want to access the CFP or submit a session to the CFP, we're using pay-per-call to do that, so please do submit your sessions. If you want to get your Java user group, your local Java user group involved, get your Jug leader to submit a session on this Google form just linked here. And you can of course register as well, so simply go to the meetup.com page or click this link here and it will take you straight here, and you can click RSVP, which will be just over here. I'm obviously already going. We've already got 30 people going. I only actually announced this 10 minutes ago. Last year we had about 4,000, I think, RSVP and about 10,000 viewed. So definitely one you want to keep an eye on. So RSVP to that now. And without further ado, Chris, I'll pass over to you. So if you'd like to screen share.
Screen share, yeah.
We can get going.
Does that work?
That looks great.
Okay.
Yep.
Oh, actually, just for others as well. Actually, if you're watching this through YouTube or through the widget, if you click on the settings cog, try and pick the highest bitrate you can, and you'll see Chris's slides and demo in the clearest possible format.
So before I start, we should say that this is a research project. This isn't a product that Oracle is planning to sell to anyone anytime soon. So this is research ideas, and you shouldn't buy Oracle stock or any Oracle product based on what we're talking about. So let's talk about programming language implementations. Why do we have so many different programming languages? People get very passionate about different languages. People get very worked up about when you criticize their language, and they're very passionate about why their language is very good. Why can't they just be one ultimate programming language? Why do we need more than one programming language at all? Why do we split our effort implementing programming languages? But if you ask this question on Stack Overflow, it's going to be closed as not constructive. People don't want one single ultimate programming language. They want lots of programming languages that do different things for their particular needs. And if you ask which language could be the one language to rule them all, then everyone will suggest it's their own language that should do that could be the one language that does everything that everyone needs. So I think if we're going to be pragmatic, we can see that people need different languages for different things. Different languages give you different features, different ways of doing things, different ways of looking at things, and that's good. It means that people who think in different ways can use different kinds of languages. If you come from a mathematical background, then something like MATLAB makes a lot of sense to you. If you come from a simulation sort of background, then object-oriented programming makes a lot of sense to you. We want to let people use the language they want to use. But what's the problem with that? The problem with that is that implementing languages is a lot of work. It's really expensive. It takes a lot of time. It takes a lot of expertise. And the problem with that is that not everyone's language is as fast as we'd like them to be. So this is a whole set of different languages, and it's a summary of loads of benchmarks from the computer language benchmarks game on those different languages. And what we show here is this graph is logarithmic. So each one of these lines is 10 times slower. So 10 times slower, 100 times slower, 1,000 times slower. Now the actual results here aren't the important thing. I don't want to quibble about exactly how fast particular languages are, but this is broadly how different languages are. So a language like C is very fast, and a language like R, which is a mathematical language, is much slower. So someone who programs in R, unfortunately, they get much lower performance, even though they'd like to use R because it does what they do well. Most languages sort of sit in the middle. So Perl, PHP, Python, Ruby, Smalltalk, all sort of a similar level of performance. Something like JavaScript is faster, but that's because of Google spent tens of years, I presume hundreds of millions of dollars, lots of really specialized people to make it really fast. And it's got down sort of more towards the level of Java, going towards C and C++, but it's taken a huge amount of effort to get there. What we'd like to be able to do is to say to people, you can use the language you want to use that's correct for your environment, that you're skilled in, that you have libraries in. We want to let people use that. But we want to be able to give them that performance, that same performance they can get on different languages, down to the level of sort of JavaScript, Java, and C. So how does language implementation work at the moment? Well, when someone comes up with a good idea for a language that they want to build that does things the way they need it to be done, the first thing they do is they prototype a new language. So they build a parser, and they build something like an abstract syntax tree, which is a way to represent a language using a data structure, and they interpret that by walking it using something like the visitor pattern. And then they start to realize that if people want to use this language, then they need to make it a real language. They need to improve the performance a bit. So they write a real virtual machine, perhaps using C, C++. They may still use an AST interpreter, but they spend a lot of time implementing things like the runtime system and the garbage collector. People start to use the language, and they find it useful, but they complain about performance. So then we define a bytecode format, and we write a bytecode interpreter. Performance is still bad, so then people write a JIT compiler. They include the garbage collector. But by the time we get down to the bottom of this chain of things to do, that's the point where we're spending hundreds of millions of dollars to do that. And it's not realistic to do that for all the languages we'd like to do it for. What we'd like to do, what the work at Oracle Labs on Truffle and Graal and our Polyglot VM, which is the GraalVM, what we'd like to be able to do is let people prototype a new language in Java, in a high-level, safe language like Java, using the simplest methods, so using an abstract syntax tree interpreter, and to have it already be fast. So to have everything else happen, the real virtual machine, the garbage collector, the JIT compiler, everything like that, to come just for free based on you having done a prototype. So you just do the easy bit and everything else comes automatically for free. That's what we'd like to be able to provide for all languages, so that the languages people want to use, languages which have less money behind them, perhaps like R, they can get a really high performance implementation for that language without having to put all that effort and money in. So if you don't know anything about how language is implemented, let's say we take a simple expression that in some imaginary language, so it's x plus y times z, that gets passed to a data structure we call an AST, and it's simply a tree that represents the operations that we want to do. So it makes some things explicit that were implicit before. So here, this tree tells us that we want to multiply y and z together and then we add X to that. So it sort of encoded the precedence here. And then we talked about a bytecode format. That means we create a very simple language that represents the program. So we load local X, Y, and Z, then we multiply them together, then we add them together, and that's what Java bytecode looks like. And that's also what Python bytecode and Ruby's internal bytecode looks like. And then to get high performance, we compile that to machine code, which is the thing on the bottom right. Now, the conventional approach to implementing languages on JVM, and let's talk about the Graal and truffle approaches and how they differ. So there's already implementations of these other languages, a lot of them on top of the JVM. So I said that we want to make all these languages fast, and aren't we already trying to do that with the JVM? So if you use Ruby, there's JRuby on top of the JVM. There's Jython if you use Python. If you use R, there's Rengen. And we said originally years ago that these languages are going to be nice and fast by running on top of the JVM. The conventional way that the languages do this is they emit JVM bytecode, similar to what the Java compiler does. So they're like alternative front ends to the JVM that emit JVM bytecode for these different languages. So why doesn't this quite work as well as we'd like, and why are we building a new system to do it instead? What the JVM does is, for this set of things you have to do to implement a language, it takes away the last one. So you emit JVM bytecode, which is like this linear set of instructions: load X, load Y, load Z, multiply and add, and it does the JIT for you. It turns it into machine code for you. But you still have to do the work to emit that JVM bytecode and to make sure you're emitting good quality JVM bytecode. The reason why this doesn't always work as well as we'd like is HotSpot, the implementation of the JVM a lot of people use, is a big black box. It's written in C++. It's a really complicated piece of engineering. So I have a PhD on implementing languages, and I work on them for a living. And even I find the internals of HotSpot extremely intimidating to work on. If you think your code bases are difficult, you should try looking at HotSpot sometime. It's old C++ code. It's very, very complicated. And all the languages which work on top of the JVM, the only thing they can do is they can pour bytecode into the top of HotSpot. That's the only interface they have. You can pour bytecode in and you say, this is the bytecode version of my R program or my Ruby program. And within HotSpot, there's a JIT compiler, which is that bit which turns it into high performance machine code. But it's inside the black box. You can't reach it directly. There's a sort of route from your bytecode that goes down towards the JIT eventually, but you can't control how your code is compiled. There's no feedback mechanism. There's no easy way to observe it at runtime. And sometimes you'll pour bytecode in, it won't even get JIT compiled at all. And if you speak to people like Charlie Nutter, who works on the JRuby project, he spends a lot of time trying to understand what HotSpot is doing with his bytecode, how to emit bytecode that HotSpot will do the right thing with, and trying to understand how it goes into HotSpot and how it's used. But it's a black box. It's hard for him to see into it to see what it's doing. What we're doing in the Graal project is we've taken the JIT, so that part of HotSpot which turns JVM bytecode into machine code, and we've taken it outside the black box. So normally the JIT is written in C++ and it's hidden in this really complicated code base. We've implemented a new JIT compiler using similar techniques, but it's written in Java. And instead of being inside HotSpot, instead of being inside the black box, it's now simply a piece of Java code like any other. Now, it may sound really complicated to say that we've written a JIT in Java. It may sound like the sort of thing that's not possible to do. But all the JIT compiler needs to do is it needs to get your JVM bytecode, which is a list of bytes, and it needs to emit machine code, which is also a list of bytes. It needs to do a few other things in practice, but in general, it's a pretty simple interface. You give it bytecode, and it gives you machine code out. Just because Java is a high-level managed language doesn't mean it doesn't work for writing compilers. It's fantastic for it. All we have to do is output a set of bytes which get installed, and that's all we need to implement a JIT. So it's not outside the realms of how we think the world works to be able to write a JIT compiler in Java like that. And because it's in Java, we can use it as a Java library. So we create it not just as a JIT compiler that works within HotSpot, we create it as part of a library, we give it an interface. And then Truffle is the system which talks to Graal on your behalf. So you write a language that uses Truffle, which is a language implementation framework, which I'll talk about in a bit more in a minute. And that talks to this Graal compiler, which is a JIT compiler written in Java on your behalf. And because the interface between the two is Java, it can be a rich interface. We have methods that say, what's happened to this? I want you to compile this way. I want you to do this with this. I want you to install this optimization pass, things like that. That can all be installed via this Java interface rather than just pouring bytecode in. So it's a rich interface, and that allows us to do a much better job of compiling languages like Ruby and JavaScript and R.
Quick question from IRC, Chris. In terms of the naming, where did the naming come from? Is there a religious connotation, or for both Graal and Truffle?
Graal, yes, is the Holy Grail. And Graal is, I think, how they pronounce Grail or Holy, how they spell Grail in Europe, in places like Austria, where the project started. So we're saying it's the Holy Grail of compilers, to have Java implemented in itself is what we'd ideally like to do. So in some ways, it's like a philosophical thing. We'd like to have Java implemented in Java. That seems like a nice exercise to do. And then at some point, we realized that actually, no, it's got an engineering benefit in that if it's written in a high-level language, you can control it using a rich interface that's more complicated to do when it's written as really low-level system code. So it started off as an academic exercise. Then we realized the potential for it. Truffle is called Truffle because it's like it's Truffle the chocolate, you know, the little round chocolates you get. When I show how it works, you'll see how the metaphor applies, but it's like a box of chocolates, so you can pick the ones that you want that taste nicest to you. Make sense?
Awesome, thank you.
So for this system of implementing languages, we said the JVM took away the part of generating the machine code, and Graal and Truffle take away the part of generating the machine code and generating the bytecode. And Truffle uses Graal on your behalf to compile an AST interpreter to high-performance machine code. So we've taken away the job of having to generate JVM bytecode and pouring it through that really tiny interface of talking to the big black box. So this means the technique we're using to implement these languages is a whole level simpler, a whole conceptual level simpler in implementing programming languages. So I'm going to talk about some big complicated things today, but keep in mind that really they allow you to make everything simpler. They allow you to do language implementation using a whole simpler technique than before. So Truffle, we've said that Graal is our JIT compiler and it has a Java interface, but it's hard to use that JIT compiler because it's still a complicated piece of engineering. So Truffle is the framework that sits on top of Graal and allows you to implement a programming language that uses Graal. So ASTs, we said that an AST is a way to represent a program. It's a tree data structure, and it makes things that were implicit in the source code, such as precedents and high-level syntax that makes things easy to understand. It sort of removes that and makes it all explicit as a data structure in memory. So we had the example before where we have x plus y times z. We then turn that into a tree which says explicitly what order to the operations in. So the plus gets its data from the x and from the multiply, and the multiply gets its data from the y and the z. And to execute it, you go to the bottom of the tree and you produce those values and move back up to the top. The trick with Truffle is that it's what we call self-optimizing. So AST interpreters are normally slow, and people don't want to use them because of they're generally slow, and then they move on to using more complicated techniques. We're allowing people to stay with the simple techniques by making it self-optimizing. So when you create your tree data structure, which represents your program, you emit it in what we call an uninitialized state. So all the nodes that represents data and operations in your program start off as uninitialized. Now the idea is, as the program runs, we start to find types in the program automatically. So in a JavaScript or a Ruby program, when you have an add, it could add together almost anything. And this is part of the reason why people say JavaScript and Ruby is slow, is that an add could add together a double or an integer or a string or whatever. It could do almost anything in practice. What we do is when you emit an add operation from the parser in a Truffle language, you emit it in an uninitialized state. And the first time it executes, it looks at what types it's actually getting, and then it converts to be a node which handles that particular type. So your uninitialized add node will become an add integer node, or an add double node, or an add string node. And this is the first part of building a high performance language, is that you profile the program like this and figure out what's going on. But using this technique, the AST can sort of profile and specialize itself and become optimized over time. Now, people say that an add operator may see integers to start with, they may suddenly see a string later on. And that's okay, that the types can transition towards a generic type which can handle anything. But in practice, most real programs see a particular type in one place almost all the time. So we can say that this node will handle just integers. And if it gets something that's not an integer, then it says, hang on, I'll handle this in a different way. But it's prepared for that case where it sees an integer, and it makes that particular case nice and fast. So over time, your AST becomes strongly typed, even though you've written in becomes statically typed, even though you've written it in a dynamically typed language. So your program says that I know I'm going to add together integers here. I know this could have to add together any particular types, or I know its division works on doubles. And that means you can start to make it more high performance because it's not having to repeatedly check what types it's getting. So we take a dynamic type language, and we make it sort of statically typed, but able to handle anything through a mechanism we'll talk about in a second. But the step we do then is we compile that to machine code. We take all the methods that are involved in executing your Java program, so all the execute methods that walk that tree in a sort of visitor pattern and perform all the operations of that tree, we take them and we inline them all together, and we constant fold them all together, and we produce a single piece of optimized machine code for your AST of your program. We do this using a technique called partial evaluation. Now, partial evaluation is a very, very theoretical topic, but if you look for a talk by Tom Stewart called Compilers for Free, he's got a very understandable summary of it. But I describe partial evaluation as just constant folding and inlining. So if you imagine you've written a Java interpreter for a particular language, we take all the code that's involved in interpreting your language, and we constant fold it with the program. So you have your AST, which is all the code for executing your program, and then you have the data, which is the program itself, and you constant fold them together, and you get a program that is the compiled version of the language. Now, we said that we're doing this for dynamic languages like Ruby and JavaScript. So if I've compiled a program that expects to be adding together two numbers in a Ruby program, and suddenly I give it a string, what we do then is we can jump from the JIT compiled optimized code back into the interpreter, and we can keep executing there. This is called de-optimization. The JVM does this already. For example, if you, I think the best classic example is if you have a interface which has just one class implementing it, then, and you call methods on that interface, there'll be direct calls to the methods in the class. But then if you class load a new implementation of that interface, then it can't make those direct calls because there could be a different implementation of the interface where before it was just seeing the one. And it uses de-optimization to implement that. It jumps from the compiled code back to the interpreter. And then we can adapt to the new types we're seeing. So where we were seeing integers, now we're seeing doubles. We can recompile using those changed types. So we can continue to handle any types, even though we've compiled, because we can jump from the compiled code back into the interpreter. Now, your program is made up of multiple methods. Each of those methods is a little tree of code, this little AST, and together they form a graph because of the methods call each other. So where I've got one of these circles, each of these circles is like a method, and one of these calls from one method to another is one of the big black arrows, and they call from one AST to another. Now, the really clever thing is we can start to do quite complicated optimizations that normally are implemented deep within a compiler. We can do those at a high level. So for example, if we have a really frequent call from one method to another, we can inline that call by creating a copy of the AST and sticking it on to where it was before. So something before that was complicated to understand and was hidden inside the JIT, we've made that explicit and made it easy to understand. Where you had an AST, we can simply copy and paste it to do inlining. So we've now inlined this method into the other one, where before we had a call. We can also do something similar for types. So if you have one method that is called with lots of different types, so call with an int or a double or a big integer, what we can do is we can say we'll create multiple copies of that method by simply copy and pasting the AST which implements it. And then each of those methods can type specialize for the particular type which is going into them. So things which were complicated and hidden inside the JIT before are now made visible to the person implementing the language, which makes it a lot easier to implement sophisticated optimizations that you need for these high-level languages. And then we can do inlining after we've done that type specialization as we had before, simply again by copy and pasting the tree. Okay, so that was quite technical, but it gives you the foundation I need to talk about the interesting stuff. What I'm going to talk about now is how you see this as a user and what the user might get out of this in the future, remembering that this is just a research project, not a product. So we've got this really simple API. This is Ruby language. And we've written a system that lets you eval source code from another language from within Ruby. So this isn't anything massively new. People do this already. But this eval statement, like eval in JavaScript or Ruby, but this one takes a MIME type, so application, whatever language, and you give it source code. And then we have two other primitives. We can let you import a name, so a function or something from another language, and we can export a name to all other languages. We have exactly the same interface in JavaScript. So in JavaScript, you can eval code from another language, you can import, you can export. So really simple 3 calls there. So as an example, from Ruby, I can say I want to eval code written in JavaScript. I want to eval 14 plus 2, which gives me 16. And we've got the JavaScript part and we have the Ruby part. It's a bit unfortunate, though, that the JavaScript part is hidden inside this string. So the Ruby part, the outer one, is sort of privileged in that it's well, the simple example here is it gets syntax highlighted, but also it's not written. I don't have to do things like string escaping to use unusual punctuation and things like that. So we can expand this a bit, and let's say I want to define a add function in JavaScript inside Ruby. So I define my add function in JavaScript, and then I export that called add, and then in Ruby I can import it called add, which gives me a function I can then call. And now we can start to see this problem of having to write things inside a string gets a bit more problematic because it's split across lines now, and it's starting to be even more awkward. So the JavaScript is still hidden within this string, and the Ruby part is the outer part is still considered sort of more important here. So as a demonstration of what might be possible in GraalVM in the future is I've extended our implementation of Ruby to allow you to write JavaScript inline in the Ruby program. So what we now write is I write the JavaScript function, add, and I then use it from Ruby. Now what we have here is the first 3 lines are written in JavaScript, and then the next line is written in Ruby. But I didn't say anywhere, now I'm writing JavaScript, and then now I'm writing Ruby. I simply write a JavaScript function, and then I simply write Ruby code afterwards. So now there's no one language being more important than the other. There's still an outer language, which is really Ruby. But I can now simply, if I want to use a JavaScript function, I can just copy and paste it and stick it inside my Ruby code like this. So those are the 2 separate languages, but neither is particularly more important than the other. So this works with data as well. So say we've got a JavaScript object which forms a prototype and it's a bit like a class therefore. So function point takes an X and a Y. And I have a JavaScript function which creates a random array of points. I can then call that random points function from Ruby, and I can access the JavaScript array from Ruby using the Ruby syntax for arrays, and I can print out the value from X and the Y from that point, just doing .x and .y, which then gets it from the JavaScript object. So I'm not just doing a call here, I'm then accessing an array from JavaScript from Ruby, and I'm accessing JavaScript object properties from JavaScript from Ruby. So the top part is JavaScript and the bottom part is Ruby, but they're working together and they're sharing functions and they're sharing objects values. Now, I said that sort of thing can be done before. Most people haven't done allowing you to put the languages right alongside each other, but you can do the eval thing at the moment. But the problem with this is performance. So it's like going back to where I said we've got these different implementations of lots of different languages, and the problem is they don't all have the same performance. So you want to use a language like Smalltalk, but the performance is poor because nobody's paying to make it fast. So you're limited in what you'd like to do by the performance. And the same thing here. I'm going to show you what the performance of this interop, this polyglot programming is, and show you that it's not as good as we'd like. So what I have here is, this is some Ruby code from a image processing library that someone wrote in Ruby. So some high performance Ruby code that processes an image. I think this is from the Ruby psd.rb library. Actually, it's for processing Photoshop files, yeah. So it does some things to convert CMYK color space to RGB, and it does it in a loop for lots of random values. And at the top, we have this method clamp. And what that does is it clamps a value, num, between a minimum and a maximum. And they've chosen to do that by creating an array of 3 values, sorting the array, and taking the middle one. And you can see how that's probably not going to be very high performance. So I've turned this into a benchmark by writing this bit at the bottom, which runs a loop and warms the program up, and then it reports the number of iterations per second. And I've got these random inputs. So I haven't written constant values, I've written random between 0 and 255 to stop the whole thing just being optimized away. So let's look at the performance of this just in Ruby to start with. So this is just look at the performance of our Ruby implementation running this Ruby code here. So the performance on GraalVM, the number of operations per second, we looked at the standard implementation of Ruby, MRI on the far right, JRuby, which is the current implementation of Ruby on the JVM, using the invoke dynamic work they did to try and make the JVM support dynamic languages better, and then the GraalVM implementation of Ruby, and performance of that is much higher to start with. So in other presentations, I explain exactly why that is, but I'm just doing that at the moment to show a baseline, to show that our implementation of Ruby is fast even before you start combining languages. And it's much, much faster than the standard implementation of Ruby or Ruby on the JVM. And that's what GraalVM is giving you for Ruby before we even start talking about JavaScript. So we have a good baseline. Right, so what I did then was I said that there are already ways of evaluating one language from another in Ruby. And one of those is to use this V8 module, which is the interface to the JavaScript implementation by Google that they use in Chrome. And it's also used in Node.js. This is a high performance implementation of JavaScript. And this allows you to create a V8 context, and you can eval JavaScript code, and then you can call it. So I've replaced that one function, clamp, in Ruby. I've said I want to write that in JavaScript instead. The reason I've chosen that method is because it's right in the inner loop. It's called for each color channel of each pixel in the image. So it's called lots and lots of times. And not only have I rewritten it in JavaScript, I've actually slightly simplified it. So instead of creating an array and sorting it and taking the middle value, I now simply do, if it's less than minimum, then it's the minimum. If it's greater than the maximum, then it's maximum, else it's the number itself. So if we run just Ruby, the standard implementation of Ruby, then it gets 300,000 operations per second. If you combine it with JavaScript, then it's only getting about 20,000 operations per second. So it's got slower, even though I've written slightly more efficient code, but because I've written it in a different language, the performance is really poor. And this is the crux of the problem we want to solve with Polyglot in GraalVM. To make, when you start to use a Polyglot environment, if you want to do that, if you think that's the best thing to do to solve your problem, you then pay the cost in performance, and it's a huge cost in performance. So V8 is a really, really good implementation of JavaScript, but because you're using it from Ruby and you're going from the Ruby to JavaScript, the performance is really limited. If we stay on the JVM, perhaps that'll solve our problems. So if we've got lots of different implementations of languages on the JVM, perhaps they can all work together and compile together really well. That's one of the things people said would happen with things like Invoke Dynamic in the past. Well, there's an implementation of JavaScript on the JVM called Rhino. So in the same way as we created a V8 context, we can create a Rhino context and do exactly the same thing. Well, actually, the performance here is still really poor. So if we run JRuby plus Invoke Dynamic, we're just running the Ruby version, then we get around 5,050 iterations, that many iterations per second. And then if we use Rhino also on the JVM, then we get another performance drop when we start to use JavaScript as well. So even though they're both on the JVM, even though they're both emitting bytecode, you still get a huge performance cliff when you want to use more than one language. If you've got a good reason to use more than one language, such as if you've got a library that's written in JavaScript you want to use from Ruby, you pay this huge cost to do it. And the same thing applies for Nashorn. So Nashorn is a more recent implementation of JavaScript on the JVM. This does use Invoke Dynamic, Rhino doesn't, and we still get a performance cliff. So saying I want to use Ruby and JavaScript, and I'll try and use Nashorn. So two really competent implementations of JVM languages. There's still this performance cliff when you try and integrate between them. Right, so in our solution, we can improve it because we don't have to write that eval for JavaScript anymore. We can simply write JavaScript code alongside the Ruby code. So the code looks a lot better to start with. And here's the fantastic thing. The performance of running just Ruby and running Ruby with JavaScript replaced for one of the methods on the inner loop, on the GraalVM, the performance of the two is exactly the same. So now we've removed that cost of saying, if you want to use JavaScript in your Ruby program, or if you want to use R in your Python program, or you want to use Java in your Ruby program or something like that, there used to be a cost. And what we've done is we've removed that. So combining languages now is zero overhead. There's no cost at runtime for peak performance to use multiple languages together. And that's something which hasn't been possible before in any other implementation of programming languages. So if we look at all the other implementations, not only is GraalVM fast at running just plain Ruby, but the performance doesn't change when you add JavaScript, and it completely goes to the top of all the other combinations of languages. And this graph is so hard to read that if I can put it in logarithmic format as well, and you can see that we're 10 times, 100 times, 1,000 times faster than other combinations. I'll skip over these. No, I'll talk about this here actually. So the reason that this can be so effective is that we talked about inlining from one method to another because everything's just an AST. So when you have a frequently executed call from one method to another, we can simply copy and paste the AST to inline it and make it fast. And that's the situation we have here. And we've got a Ruby loop that's trying to execute really fast. It's having to make a call to JavaScript. And because that call is going from one language to another, and because of the normal systems that aren't allowing it to inline that method, that's why it's slow. So we've got this critical call that's happening right in the inner loop. And because it's going from one language to another, in every other system, it's slow. So there's that interface point where it has to stop everything and say, right, I'm not doing JavaScript anymore. I'm not doing Ruby, I'm doing JavaScript. I need to convert this, figure out what I'm doing here. That makes it slow. But because we've got implementations of both Ruby and JavaScript, both on top of Truffle, both using this simple high-level way to represent languages, that means we can do things like inline the two languages together. And that's what's happened here to make this performance as good as being just Ruby staying in one language, in that we can inline the JavaScript code into the Ruby code. We can compile them together. And that's because of, to the runtime system, to Truffle and Graal, it doesn't even know what language these trees came from in the first place. All it knows is it has a couple of ASTs, and it can inline them together, and it doesn't care which language they came from. And so the performance is the same when we had just pure Ruby to when we have Ruby and JavaScript together. So how effective is this in the extreme? When we take it, let's drill down and see how is this really managing to run JavaScript and Ruby together so fast. So what I've got here is on the left, I've got a pure Ruby code that runs a loop that has a while loop that adds together n times. So if you give it sum 1,000, it will add together 1,000 times. And we do that in a big outer loop. On the right, I've done the same thing, but I've written that sum in JavaScript, but the outer loop is still in Ruby. So what I'm going to look at is these two loops here. We've got a loop written in Ruby and a loop written in JavaScript, but they're both doing the same thing. And the magic of Truffle and Graal is we can compile those two things to exactly the same machine code. So because we've written a high-performance JIT compiler, it works, that's universal. It can work for Ruby and it can work for JavaScript, and it can generate high-quality code from both. So this loop, which does a while from I up to n, and it adds together n onto a each time, we generate machine code which literally does add something. It jumps if it overflowed, because of both languages have overflow detection. If you overflow an integer, we increment a counter. We compare it to the end of the loop, and then we jump back to the start if we've reached the end of the loop. So that's our first point, in that we've got a really good JIT compiler that can generate really tight machine code from high-level languages, and it's so good that it can generate pretty perfect machine code for both JavaScript and Ruby. And Ruby's had never had a JIT that's that powerful before. JavaScript has in V8. But this is the first time I've had a JIT that's this powerful for Ruby, and it matches JavaScript's performance exactly here. What I've done here is I've got that loop, that sum loop, but I've replaced where I add together n onto a each time. I've now written that as a Ruby function or a JavaScript function. So now the outer loop is always Ruby, and just the add operation is either done in Ruby or JavaScript. And again, we can produce exactly the same machine code from that. So before, where we were having an add which was in Ruby and was inlined, now we've got an add that's coming from JavaScript, and we've actually inlined that into the Ruby code. So if we look at the particular machine code for this, in the case where on the right-hand side, where we had a Ruby loop that was calling a JavaScript function, what we've got is this add and this jump on overflow, that comes from JavaScript. And it's in the middle of the machine code for Ruby, but there's no way that you notice it. So you just see a stream of instructions, and it happens to be that this add and this jump on overflow comes from JavaScript, even though it's embedded in the middle of this machine code that came from Ruby. So what I'm trying to emphasize here is this is how tight the integration is, because if both systems are running together on Truffle, that we can completely inline and remove all sign whatsoever that a code came from a different language right into the middle of the Ruby code. And the benefit of all this technical stuff for the end user is that you can use JavaScript from Ruby, or Ruby from JavaScript, or Python from R. You can use whichever language is appropriate, and you don't have to worry about the cost of going from one language to another. And this is why we call it a Polyglot VM. It runs all these languages and it runs them all together. So what I do now is just jump into the Graal source code a tiny bit. I want to dispel this black box idea. People who use the JVM, who don't do any kind of systems programming, they do applications programming on JVM, they've probably never had reason to look inside HotSpot. And you know what, I wouldn't actually encourage them to do so, because it's really nightmare code, and it's very hard to work with. But I would encourage them to stick their heads inside the Graal source code. And if you know just a tiny little bit about compilers, then you can understand and see what it's doing, even if you aren't an expert. And I think it's the first time in our community we've had this sort of ease of access to understanding what the compiler code does. So I'm just going to point out a few things. And one of the great things is I'm going to do it mostly by just navigating to implementation in my IDE. So we're looking at an example there where we're adding together numbers. So I've got the implementation of Ruby here in my IDE. I'm going to open the implementation of, oh, it's a presentation mode. So this is the implementation of add for Ruby. written in Truffle. Now there's a whole lot of complexity here. What I've decided to do is not to hide the complexity, to pretend that it's not there, but I'll pick out what's interesting and relevant. So what we have here is this is the code for a Truffle node in Ruby that adds together two integers. And it's like overloading. We can say this version adds together two integers, and this version here adds together a long and a double. And you can see that we call it Truffle because it's like a box of chocolates. This one is this flavor for integer, and this one is this flavor for a long and a double. But what I'll point out here is where we add together two integers is we do math add exact, because that adds together two integers and also detects overflow. When you add together two integers in Ruby or JavaScript and you overflow, it converts them to a different type. So let's start off with math add exact. Now what I'm going to do is I'm going to jump to the Graal source code now. So I'm moving to Eclipse because I've got it loaded in there. And before I start navigating to the definition, I'm just going to do one piece of magic, which is I know for a fact that integer add exact is implemented in the compiler in something called standard graph builder plugins. So don't worry about what that means, but I can tell you that when you call math add exact, the compiler goes here. So what I'm showing here is I've got the Graal compiler source code loaded. I'll show you where it comes from later on. But what we have is a Java program, and when I call add exact, I get an integer add exact node created. So this is the object that the Graal compiler creates to represent that operation when it's compiling it. And again, there's lots of complexity here because it's a real production compiler. But I'm going to show you something neat, which is if we poke around in this, then I can see something called create split. Create split is what happens when it simplifies this operation to be lower level operations. And I can follow this to integer add exact split node. And I can jump up here. This is the general integer exact arithmetic split node. And it gets interesting when I jump down here. So this is the part of the compiler which generates the actual machine code based on what your program does. And I'm going to follow this emit overflow check branch. I'm going to go to its implementation. I'm going to follow that again. I'm just going to open implementation. And I get a choice here, and I'm going to the AMD 64 one. So this is the architecture for my particular processor. I'm going to go to this creates a branch operation. And then I get here for emit code. This calls something called JCC, which is the name of the machine instruction for jumping if a condition is met. So if we jump on overflow, then I want to JCC. I'm going to the implementation of this. Follow a bit more in direction, and this is what I want to show you. So I showed you how we were in the Ruby implementation about how we called a method which is part of the JDK, which is math add exact. I showed you how that generated an object in the compiler, and I followed it through a load of implementation methods. And what's cool is these are the actual bytes which are emitted to do a jump on overflow on AMD 64 machine code. So jumping back to my slide for a second, we said that we generated an add and a jump on overflow. This jump on overflow instruction is emitted from Graal here with these emit bytes. So the great thing about Graal from exploring how compilers work is you can open the Java source code of Graal in Eclipse, and you can follow what the methods do. You can go to the implementation of methods, and then you can get all the way down to where it's actually emitting the machine code bytes for doing those operations. I know what it does and why it does it. Doing it is complicated, and I know almost someone's going to be able to follow why it does that stuff. But isn't it fantastic that you can go all the way down to where the bytes are actually emitted for the machine code and stay in Java? And no point of having to go down into C++ to see how that works. So this is part of the philosophical interesting thing that we've implemented a Java compiler in Java, and I mean machine code compiler, a JIT compiler there. And the practical benefit is that performance we get on combining multiple languages. So what is this for? We're not really suggesting that people would routinely write alternate methods of their programs in different languages. I'm sure some people are probably criticizing this in their heads now, thinking, that looks like a huge mess. I wouldn't want to write one method in JavaScript and then one in Ruby. I have enough legacy problems with systems that have been used in different crazy ways over time anyway. So I'm not really suggesting that people would want to routinely do that. It's more about removing the consideration of performance from the decision to do it if you do want to combine languages. So if in your business environment, in the code base you've got, in the time you've got, and the things you're actually trying to achieve with your lives, if you do want to combine languages, for example, you've got some JavaScript format function that you'd like to use from Ruby, this allows you to copy and paste it without having to worry about the performance. So if you've got a good reason to combine languages, this means that it's now possible to do that without having a big performance impact. This could make it so that all library ecosystems are available to all applications. So one of the great things about Ruby is it's got a fantastic set of libraries in gems. JavaScript's also got a fantastic set of libraries. But if you program in some new language, you may find you don't have those libraries available to you. It could be great if you know there's a good Ruby gem for doing what you want, but you program in JavaScript or Node.js. You could pull this into Node.js using this technique. It may be useful for unifying a front end and a back end. So if you have code on your front end, you think, actually, I need to do that when I generate a report or something on the back end as well. Well, then you can pull the code across to do that. And it may be useful in enhancing legacy applications and incremental changes. So if you've got a big old R program and you want to start doing your statistics in Python instead, then you could slowly sort of transition it to Python, sort of one method at a time almost. So GraalVM, is it an abstract thing or is it something you can actually use today? GraalVM is our name for the package that includes everything you need to do this kind of stuff. So the GraalVM is like a new way of doing a JVM. So GraalVM includes a JVM. It includes support for Java, but also includes support for JavaScript and Ruby and R and other languages in the future. And you can get this as a binary tarball, or you can get the source code for most of the components in it, and you get this for either Mac or Linux. The alternative way to do it is with Java 9, you should be able to use this on an unmodified JVM. So GraalVM includes a modified JVM that includes an interface that we need to install a different JIT compiler. On Java 9, the great thing is because everything's written in Java, the compiler is written in Java, the language implementations are written in Java, and Truffle's written in Java. There's HotSpot at the bottom, which is C++. And what we've done is there's a little interface that goes from Graal into HotSpot. And we call that JVM CI, the JVM compiler interface. And the great thing is we've put that into Java 9. That's part of JEP 243, it's called. And when you see lists of cool new things in Java 9, I've never seen this included on one of them yet, but JVM CI, the JEP 243, is an API in the JVM that allows you to install your own JIT compiler instead of using the standard one. And that ships with Java 9 when Java 9 is released. It's already been merged in. And then you can get everything else however you want. And you can install Graal as a new JIT compiler using that special interface. It's like using a Java agent or something like that. And you can get that from Maven or OTN. And OTN is how we're distributing the GraalVM at the moment. If you search for Graal OTN, OTN is the Oracle Technology Network. It's where you can get previews of Oracle applications, things like that. That's the actual URL on the bottom right, but it's easier to search on any search engine for Graal OTN, you'll find it. And you can download this technology and experiment with it today. But most of this is open source as well. So at the moment, the JavaScript implementation isn't open source, but the Graal compiler, the JIT compiler, the Ruby implementation, the R implementation, the Java implementation are all open source on GitHub. So if you search for GitHub GraalVM, you'll find that, or the links on the actual precise links on the bottom right. And you can do the demo I've just done yourselves. If you download the Graal JIT compiler, you can load up into Eclipse or any other IDE, and you can explore how it works, and you can see where it emits machine code bytes. Even if you don't know much about compilers, it's still fascinating to just poke around in there. Even if you just do it on GitHub, poke around and see that we can implement a JIT compiler in Java and we can go all the way down to omitting the machine code bytes without leaving Java. You don't need to use a low-level language to do it. That's my Twitter handle, Chris G. Seaton. As I say, github.com GraalVM is where all the open source code is located. There's a Gitter room. You can come and speak to us directly. If you're trying to use GraalVM for something and it's not doing what you want, you can go on there and you can speak to the researchers and engineers directly. And if you search for OTN GraalVM, you'll find the binaries you can download and start trying today. So acknowledgements, this is a really large engineering effort that Oracle Labs is working on. Those are some of the people. That's a longer list of the people working on it. I think there's about 30 to 40 people working full-time on GraalVM at the moment. So it's a research project, but it's a big research project working towards some big goals and some big things in the future. I've cherry-picked a couple of things which I think are really cool to talk about. They sort of demonstrate how Graal works, but there's a whole world to it more in GraalVM for supporting polyglot languages and had time to talk about. As I say, it's not just me working on it. I work on the Ruby implementation. There's all these people working on other parts of it. Thanks very much.
Yay. That was a fantastic presentation. Thank you, Chris. I hope Simon will be joining us in a moment. I must say, like, there are not so many questions in the IRC chat, but I guess I can ask those. There's actually like just one question, but I think you answered that later than it appeared. So isn't OCaml or Haskell suitable for implementing the compiler, right? So it has all kinds of powerful features. So
yeah,
very beginning of the presentation.
So ML, if people don't know the history of ML, I think it originally stood for meta language. And one of the purposes they had in mind was implementing other languages in ML. And Haskell comes from the functional tradition that started with ML. So that's probably why they mentioned Haskell and ML. And they're really good for describing programs because they're fantastic for manipulating tree data structures and things like that. We do have some practical concerns in Graal, in that Graal is still a JIT compiler. It needs to emit code quickly. And it needs to be able to therefore work with mutable data structures. Now, I'm not going to argue whether you could do the same thing as efficiently with immutable data structures as something like Haskell, or you could use references to make your data structures mutable. But I think in practice, Java's approach of using mutable data structures to represent graphs, things like that, works really well here. The other thing is there's lots of fantastic tooling around Java. It's really easy to take the programs and to manipulate them as data. So one of the things I didn't want to talk about today because of the time, because there's a whole world of cool things to talk about, is there's a tool called the Substrate VM. This allows us to take a Java program and compile it ahead of time. You may have heard about ahead of time compilation coming in Java 9 anyway. This is a different thing in that it really produces a single standalone executable from your Java program. And we can use this to make versions of our language implementations that don't need a JVM to work. So my implementation of Ruby, written in Java, that normally runs on the JVM and uses Graal, we can actually run that without a JVM by using this ahead-of-time compiler. And the ahead-of-time compiler is possible to engineer partly because of the JVM can manipulate its programs as data quite easily, because you can take the bytecode and you can manipulate them and things like that. So Java's a good practical engineering language. Haskell's fantastic for making experiments, things like that. But Java was the environment we were working in.
That's reasonable. So another question from guest 96700. Do you have any success stories for Graal being used in production by any company, or do you think it's at this point is still very much a research project that is kind of just getting into the industry through that JVM compiler interface, maybe in the upcoming versions and so on?
Graal as a JIT compiler simply for Java is pretty complete and pretty stable. So you can run it as a compiler for your Java programs today. And I think, for example, Twitter is experimenting with running Graal as a replacement for the not hotspots, normal jet compilers on their servers where they're running very large Java applications. That's partly because of someone at Twitter used to be part of the Graal project, so they've taken some experience to do it. I think if people are looking to get more performance out of Java applications, out of Scala applications, and they're experts in what they're already trying to do, then trying Graal might be the right time to start experimenting with that. For example, Charles Nutter is experimenting with writing custom optimization passes that he plugs into Graal to make JRuby faster. And he can do that because it's just a Java library. And he can write a new class that's a new optimization path and plug that into Graal and try and speed up JRuby. So it's good for experts like that to start experimenting. The languages themselves are a little bit earlier in the research cycle. So if you're a Ruby enthusiast and you want to experiment with a new implementation of Ruby, you can come and talk to us about trying Ruby out. The JavaScript implementation is pretty much done, but they still, I think they're good for looking at for curiosity, maybe not for jumping in and thinking you want to try and use them in production yet.
Excellent. I think that was all the questions from the IRC chat. Simon, do you have any questions?
No, nothing from me. I think I can't see anything on Twitter or IRC either myself. So yeah, thank you very much, Chris. It just leaves me to say thank you. This session is recorded and will be available on YouTube straight away, so we can share that on Twitter. Yeah, Chris, thank you very much for joining us today on the VJAG. This was your first VJAG session, so yeah, congratulations and thank you very much.
Thanks so much.
Oh, wait, sorry. If we can interrupt you once more, there is a very late question. Are there any plans to define something like a common language specification in the .NET world, meaning some guidelines to make languages interop easier using Graal?
Yes, so there's a protocol, an interface for how languages can interoperate. But this is a real research problem we're trying to solve. We thought it'd be fairly easy in that we could say, if you have an object and you call .foo on it, say what should happen in each language turns out to be really, really complicated. And that's a problem we're struggling with at the moment. It seems like it would normally make sense. If I call foo on a JavaScript object, then look up if there's a foo method, and if there is, call it. But in Ruby, objects can live in one of two classes on each object. You could be trying to read a field or call a method. When you start to think about all the possibilities, it starts to get really, really complicated. So it's simple for the examples I showed where you simply say .x or .y. But trying to figure it out for all possible cases, yeah, is very tricky. And it's an open problem, I think.
Okay, awesome.
Cool.
Well, thank you very
Very interesting.
Yeah, thank you very much, Chris, for quite a different session actually that we're normally used to in on the VJAG. We're normally pure Java, but this has been very, very interesting. So yeah, thank you very much, Chris. So for everyone else, we do have a couple of sessions actually on Java 9 next month, starting with Simon Ritter, and I'll post them up probably tomorrow. And yeah, VJAG 24 is up already, so so feel free to go online and sign up to that. Obviously, free conference, 24 hours, 24 contiguous sessions. Other than that, thank you very much. Have a great evening or day, and see you next time on the VJAG.
Thanks, Chris. Goodbye.
Thank you. Bye.